I'll define linear mass density of the rod. It's a thin rod. Instead of asking somewhere here on the axis here, no, I'm asking it is a certain perpendicular distance d at point P. What is the field strength due to? Get into this one. What we have to, we need one formula, no? How to generate that formula is what we have to think here. So what is the method? I'll assume a elemental mass, elemental strip. Okay, this, so we'll assume elemental strip. So let this be equal to dy. So let it be at a distance phi. Let this be theta. This angle subtended, let it be d theta. First, we'll find out due to this small element. Then what will happen? What is the mass of this? dm. This is. So let it be at a distance r. How the field will be? How the field will be directed? The field will be directed like this, no? dE. And it's a vector, no? dE bar is a vector. Okay, we have to give a generalized formula, that one. And prior to that, the ends will also subtend an angle. Meanwhile, you continue. I'll just modify the diagram. Yeah. Now, you can see this. These are the ends. I'll show in another diagram. It will become very messy. Everything will be messed up here. Now, what are these things? Alpha, beta. This is the total length of the rod. This is lambda. So what I do, I will draw a line joining the ends to the point P. And that particular line will subtend an angle alpha and beta with this perpendicular distance what we are measuring. And this is a point P. What is a dm? Dm, what we can define lambda into dy. First, due to this, what is the field strength at point P due to this small element dm. So that will define it. So that is equal to dE is equal to g dm by r. This is a magnitude. In vector form, dE bar, two components will be there, no? One x component, other will be the y component. So here we'll define the coordinate system. X, let this be y. So this will be dE x bar g dm. Just mathematics, nothing to do. R square dE. So what is this? Cos theta, shall we write? Cos theta I cap. Further, g dm, what we can write it as lambda into dE bar. A component of field will be there along negative x-axis. The other component will be there along y-axis. Component of dE bar along x-axis, dE cos theta. Component of dE bar along y-axis will be dE sin theta. Agreed? This? No. We have to lambda, let it be. So lambda is given for us rather than mass, and then usually lambda will be defined for us. So G lambda is defined. Shall I integrate? What is the biggest problem? For different elements, you assume different elements. If element is here, what is theta? Will vary. So theta is a constant or variable. And look at that one. If element is here, what is the value of R? R will change. If the element, if you bring it here, what is theta? Theta 0 and R will become D. And as you move here, R again will increase, will be greater than D. So is it R constant or variable? Yes, R is variable. Theta variable. What about dy? Yes, dy also is a variable. I can assume a length, elemental length of different lengths. No? So dy cos theta are three variables are there. This is unknown. We can integrate only when unknown in LHS, one no variable in RHS. But we have three variables. So therefore, I should search for possible mathematics. I should look for some possible mathematics where one unknown in LHS, one variable in RHS. Yes, we can simplify things here. Agreed. I think there's a one method water. So now search for what possible mass you can bring it here. So tan theta equal to y by d. The first some mathematics I'll bring it. Let me bring from corner here. Tan theta equal to y by d. Y equal to d tan theta. I'll differentiate this. dy is equal to okay. Now I'm bringing like this dy. Okay. Next again regarding r cos theta equal to d by r, or r equal to d secant theta. Let me substitute all this. dE bar equal to minus g lambda. dy will be d secant square theta d theta cos theta I cap. R square will be g lambda let's see, secant square theta d square, this everything will end up, will have minus g lambda by d cos theta I think it's good, no? Everything we brought in terms of only g lambda, they're constant. G lambda, they are constant. Only theta, d theta. So I want the field now due to upper part, the field at point P due to upper part of the rod. So theta, what happened, will vary from 0 to alpha. So what is this? This is the theta equal to 0 degree line. This is the theta equal to 0 degree line. No, if I vary theta from 0 to plus alpha, I'll get the field at point P due to upper part of the rod. If I vary the theta from d theta from 0 to minus beta. Why minus beta? I'm measuring opposite to alpha. Then I'll get the field at point P due to lower part of the rod. So what should be the limit now? So the limits here will be dE bar equal to minus g lambda d theta. Nothing to do all this, like it's all about the mathematical skills. Just how good you are in your utilizing your mathematical skills. So what should be the limit now? The limit will become minus beta to plus alpha. Let me write E bar, the resultant E bar. Why the limit should be like this? Because d theta, if you vary from 0 to plus alpha, you get the field at point P due to upper part. If you vary from 0 to minus beta, you'll get the field at point P due to lower part here. So next again, solving this is equal to minus G lambda. I cap is there, no? Here. Let me keep I cap here. So integral of cos theta sine theta minus beta plus alpha. Integral of sine theta minus cos theta minus beta plus alpha. The final equation will be E bar is equal to G lambda D sine alpha plus sine beta I cap cos minus cos alpha. So this will be cos beta minus cos alpha J cap. Okay. So this will be minus cos alpha minus cos beta. Cos of minus beta will be cos beta only. Look at this. So there's a one equation what we have ended up here. So if you can remember this, you'll be in better position so that any numericals you can solve comfortably. This is due to E bar field due to finite rod. Just notice, I'll scroll down. We'll keep this formula in hand. Okay, let's go for application. There's a theory and nobody will ask you to derive this, but you should know how to use this formula. And the first one, so let me go for infinite rod. Or select a on the bisector, we'll find out first. What about the field on the bisector? So what do you mean by bisector? There's a finite rod. So exactly on the bisector, there's a length L by 2, L by 2, linear mark density is lambda. At point P, I want the field. On the bisector, alpha should be equal to beta. On the bisector, alpha should be equal to beta. So what should be the resultant field? How it should be? So we'll cross verify whether our formula is right or wrong. We have to cross verify, no? So let's assume two small elements. See whether mathematically anywhere we are missing some terms, we should be able to identify, no? So here due to this, the field will be like this, and due to this, the field will be. So how the field? So DE and this will be DE, no? Two symmetrical elements I assumed it. So what is the net field? Net field should be only along x-axis. Are you sure? The y components will cancel out. I assume two symmetrical elements. So let me take say some phi. Let's use this formula. Alpha equal to beta because symmetry is there. L by 2, L by 2. So as I'm very sure alpha equal to beta. So there's no problem with I cap. But J cap, there should not be y component, no? There should not be y component. And how I'm measuring beta? Alpha and beta. So this is alpha and this is beta. So what I'm getting again is non-zero, no? But I know the field will be only towards left for a finite rod. the net field here will be, I'm very sure it should be like this. And I'll make things a little bit still more easier. So let this be L by 2. So that alpha and beta will become equal to how much? 45 degrees. No, this is a lambda. Okay, now you tell me what should be the field. The field at point P will be only due to what? Due to the x component. But when I go here, what is the problem I'm arising? I'm getting even y component also, but I'm very sure that only x component. So something we have to really cross check things where we are not getting suitable thing here. What is the part which we have to take care? Cos beta. Somebody is, yeah. Last step, it plus b, it must be plus cos beta, minus cos alpha. Okay, that one, yeah. Fine. Okay, now you see that. See, because this is a generalized formula, there should not be any error because all our numericals will revolve around it. So just we are cross-checking whether our formula is right or wrong. If your formula is right, then okay, I'll go for all the application because everything now what all I do just based on this formula. It's a generalized formula, I'll write it. Generalized formula for rod, for thin rod. No, I think justified alpha equal to minus cos alpha plus cos beta. Come 0 and the net will be this much. So what is the field at point P now? According to this formula, minus g lambda L by 2 sine 45 plus sine 45 I cap. So minus 2g lambda L 1 by root 2, 1 by root 2 will be root 2. What is the direction? I cap. So this will be minus 2 root 2 g lambda L I cap. Finish sure. It's all about the formula. Again, no need to take small element, integrate, solve, big headache, no. Directly take help of that formula. So due to finite rod on the bisector, what is the field is given by how much? 2 root 2 g lambda by. I assume that length L by 2. If they give some other length, then it will become in terms of alpha beta. But altogether, it generalized. I think alpha beta on a bisector, alpha beta will cancel out. On a bisector means what happen? On a bisector, what happen? Alpha should be equal to beta. So this J component will not be there. Only X component will be there. So all these are some small applications which will go for it. Okay, next after this, we'll take another one. No, a finite rod got over. No, infinite rod. Long rod it is. E bar E due to long rod. Now where I'm asking field? Anywhere here. Now what is the field at a distance D? I'll bring that formula. Let me keep this formula in the corner. Okay, all of you able to see this? Yeah. No, apply the things. What do you mean by long rod? Alpha and beta will be infinity. Alpha and beta will be infinity. So I think here I'm showing finite, but practically what happened? Alpha and beta will almost tends to infinity here. So it will be like this. Because at infinity they should meet, no? So what is alpha? Alpha and beta. Alpha will be 90, beta will be 90. If alpha and beta are 90, so then what is the net field? The net field E bar will be is equal to minus G lambda D sine 90 plus sine 90 I cap. Say any formula you derive, no, once cross check for any one condition, then you'll become, you'll be very sure about this. So this will be 1 plus 1 I cap, this will be 0. This quantity will become 0. So this will become minus 2g lambda by d I cap. I have another easy method. I'll show it later on in the end. No need to do all this much of calculation. So what is the field due to long rod or infinite rod where the end will go to infinity? What is the formula? Minus 2g lambda by d. And I will be directed towards left here. Towards the rod. It should be towards rod. But sir, is it a bisector? I think please do have common sense. Long rod, no? So is it point P, sir, on a bisector? For infinite rod, wherever you keep that point P, it will be what like? Bisector only, as it is infinite. After this, there's a long rod or infinite rod it is. Rod of infinite length. Next we'll go for semi-infinite rod. Semi-infinite, one end will be there at infinity, other end is at origin and it is having a lambda at a distance d